Einstein called it spooky action at a distance. But did he actually reject it? Is quantum time travel almost real? And can quantum computers actually make everything faster? Today, we unravel 6 quantum myths, tidy them up, bust them wide open, and reveal the beautiful reality beneath. Einstein hated entanglement. And 5 more quantum myths busted. You've probably seen headlines like "Scientists send particles back in time," but not quite yet. Here's the real story. Quantum teleportation is the process of transferring a particle's quantum state, not the particle itself, from one location to another. It uses entangled particles and classical communication. A sender, Alice, and receiver, Bob, share an entangled pair. Alice measures her particle and her half of the entangled pair. She then sends Bob the measurement result, which he uses to perfectly reconstruct the original state on his particle. The original state is destroyed in the process. Selective teleportation, or post-selection, is a statistical method used in some experiments to create the appearance of a time loop. Researchers perform a quantum teleportation experiment, but then only keep the successful outcomes, which occur a quarter of the time. By filtering out the other results, the remaining data appears to follow a trajectory consistent with a particle's state being sent to the past. Despite the intriguing name, this process does not involve actual time travel. No particle has been observed to travel to the past. The time loop behavior is a simulation, a clever result of a specific type of data analysis, not a physical reality. Imagine quantum engineers keeping only the winning outcomes, like tossing a coin and discarding all the tails. Doesn't break time, but sure looks sci-fi. And thanks to a recent quantum switch, scientists even rewound a photon state. Quantum-level rewind, not Doc Brown's DeLorean. Game changer for error correction, but human time travel? Sorry, rewind that dream. Myth 2. Quantum computers will instantly make everything faster. Quantum computers are everywhere in headlines, promising to revolutionize chemistry, logistics, even crack encryption. But they're not just ordinary computers with lightning speed. Qubits aren't simultaneously 0 and 1. They exist in a superposition with probabilistic outcomes. N qubits span a space of 2 sigma classical states. Sounds like parallel processing, but measuring yields only one outcome at a time. Repetitions are needed to see the statistics and find the correct answer. Algorithms need to be cleverly designed to amplify the right answers. Speed is not automatic. It requires innovation. Error correction and fragility of quantum states are big challenges. So yes, they're powerful, but quantum computers aren't like quantum Word or quantum Netflix. Instead, they're investigative tools for simulations, cryptography, and complex systems, and they still need smarter algorithms and tougher hardware. Myth 3. Did Einstein reject entanglement? Einstein famously called entanglement spooky action at a distance, but did he actually reject it? Let's set the record straight. Einstein, Podolsky, and Rosen, EPR, presented the EPR paradox not to disprove quantum mechanics, but to argue that it's an incomplete theory. They believed it was incomplete because it couldn't account for certain elements of reality that they argued must exist. The EPR paradox centers on 3 core principles they championed. Realism. They believe that physical properties of a system have definite, objective values even before they are measured. For example, a particle's position and momentum should exist as real, definite quantities at all times. Locality. This is the principle that a physical effect cannot travel faster than the speed of light. An action on one particle cannot instantaneously influence a distant particle. Completeness. They defined a complete physical theory as one where every element of the physical reality must have a counterpart in the physical theory. The thought experiment and the flaw. In their 1935 paper, Can Quantum Mechanical Description of Physical Reality Be Considered Complete? They proposed a thought experiment involving 2 entangled particles. When 2 particles are entangled, their properties are linked, no matter how far apart they are. For example, if you measure the spin of one particle, you instantly know the spin of the other. The EPR argument went like this. Consider 2 entangled particles, A and B, that are sent to 2 distant observers, Alice and Bob. According to quantum mechanics, neither particle has a definite spin until it's measured. Their spin is in a superposition of states. Alice measures the spin of particle A. Due to entanglement, the moment she gets a result, She knows with certainty what Bob will get if he measures the spin of particle B. According to the EPR reality criterion, since Alice can predict Bob's measurement with certainty without disturbing his particle, the spin of particle B must have been a pre-existing element of reality. Alice could have chosen to measure a different property of particle A, e.g. momentum, and in doing so, she would have instantly known the corresponding value for particle B. This suggests that particle B must have had definite values for both spin and momentum simultaneously, which contradicts the Heisenberg uncertainty principle of quantum mechanics. They saw this as a dilemma. Either the act of Alice's measurement on particle A instantaneously affected particle B, violating locality, spooky action at a distance, as Einstein called it, or both particles must have had definite properties all along, meaning the quantum mechanical description of reality is incomplete. Ultimately, Einstein, Podolsky, and Rosen chose the latter. They believed that quantum mechanics was a successful but statistical approximation of a deeper, more complete theory that would include hidden variables to account for these pre-existing properties, thus restoring realism and locality. However, later experiments, particularly those based on Bell's theorem, showed that the spooky action is real, and the hidden variables they sought do not exist in the way they imagined. He didn't deny entanglement existed. He disliked its implications. Instantaneous state collapse seemed to conflict with relativity. Bell's theorem, 1964, formalized tests for hidden variables. Subsequent experiments, starting with Friedman and Clauser, 1972, and later Aspect, 1982, repeatedly validated entanglement and rejected local hidden variable theories. Experiments like Delft in 2015 closed all major loopholes, making the spooky action very real. Einstein wasn't naive. He was seeking certainty. In science, we question. It's not denial. Today, entanglement is real, foundation of quantum encryption, and yes, always spooky. Myth 4. Relativity and quantum mechanics are incompatible. Clarify. They work in different scales. No evidence yet that they're fundamentally irreconcilable, and there's hope that future theories will unify them. Myth 5. QM is deterministic. Quantum mechanics is fundamentally probabilistic, not hidden classical randomness. The randomness is baked in, not a placeholder for missing info. Phew, we've slayed 5 sci-fi quantum myths: time travel simulations, quantum computing hype, Einstein's true stance, relativity versus QM, and sexy-sounding but misleading determinism. The truth is just as thrilling and way more useful. Which myth surprised you most? Drop a comment. Hit like if you love quantum weirdness, and subscribe to keep unraveling reality. Want part 2? Say yes, entangle me.